Hi all, in this video we will learn about principal component analysis. PCA helps to prevent overfitting by reducing the dimensionality of the data, and it makes easier to build simpler models. Here we are retaining only the most important features. So PCA reduces the risk of capturing the noise and random fluctuations which can lead to overfitting. So this PCA is reducing the curse of dimensionality and thereby it prevents overfitting. The various steps in PCA. Step 1 is to standardize the data. Number 2, to calculate the covariance matrix. Number 3, we can find out the eigenvectors and eigenvalues from the covariance matrix. Step 4, to construct the feature vector and to compute the principal components. Step 5, we can project the data onto the chosen principal components and thereby we will achieve the dimensionality reduction. Let us consider the given set of features and we are going to apply PCA to reduce the dimensions. X and Y are the features and we have 4 observations here. The first step is to find the mean. From the given set of features, we are finding the mean of X and mean of Y. Step 2 is to find the covariance matrix. We need to compute the covariance between X, X, Y, X, Y, Y. The formula to compute the covariance between X and Y is equal to 1 divided by n minus 1 summation of xi minus x bar into yi minus y bar, where I ranges from 1 to n. So n represents the number of observations and xi, yi represents the features and x bar, y bar represents the mean. The first step is to compute the covariance between x, x. The value is 14. Upon applying this formula, we can compute the covariance between x, x, y, y and x, y. As x, y is already computed, we need not compute y, x because it is going to be the same. Now the covariance matrix is 14, covariance of x, x, covariance of x, y is minus 11 and covariance of y, x is the same, minus 11. Covariance of y, y is 23. So this is how the covariance matrix is constructed. Step 3 is to find the eigenvalues. Determinant of the matrix minus lambda into the identity matrix. Here the determinant of 14 minus lambda, minus 11, 23 minus lambda. So the covariance matrix minus lambda into that identity matrix. And upon reducing this value, the determinant of this matrix, we get a quadratic equation. Now reducing this quadratic equation will give us two values, say lambda 1 and lambda 2. Here lambda 1 is 30.38 and lambda 2 is 6.62. If we want to find out the first principal component, we need to calculate the eigenvector associated with the largest eigenvalue. Here the largest eigenvalue is lambda 1, that is 30.38. So we need to find the eigenvector corresponding to this eigenvalue. Step 4 is to find the eigenvectors of lambda 1. The covariance matrix minus lambda I determinant into that vector equal to 0. Now substituting the values, corresponding values in this equation. So the covariance matrix, this is the covariance matrix, minus 30.38 into the identity matrix. This is the value. When we reduce it further, we are multiplying it with the vector v. So we get two linear equations. Now, upon reducing these linear equations, the vector is obtained as 1 minus 1.489. Now, if we want to normalize this vector, we need to find the scalar value, magnitude value of this vector. To find the magnitude value of this vector, the formula is root of v1 square plus v2 square. So 1 square plus minus 1.489 square. So when we are reducing, it is approximately equal to 1.793. For normalizing, which is equal to 1 divided by that scalar value into that vector, which is approximately equal to 0.558 minus 0.830. This is the eigenvector of lambda 1. To calculate the first principal component, we need to compute the eigenvector from the largest eigenvalue. That is what we have done previously. But this lambda 2 eigenvector of lambda 2 is not sufficient here, but still I just want to show the calculations. It's same as that of the previous one. Now once the eigenvector of the largest eigenvalue is computed, we need to calculate the principal component, the first principal component. The formula is z equal to x standardized and dot v, where this x standardized is represented as x minus mean, and this v represents the matrix of eigenvectors. So computing x standardized is x minus mean. So the first principal component is computed from this equation, that is x minus mean into the vector matrix of eigenvectors. Here we have taken the first point 4 comma 11. 4 comma 11 is taken and we are computing the principal component. Likewise, we need to compute the principal components for the other three values also, x2, y2, x3, y3 and x4, y4. Once the principal components are computed for all the observations, you can see for 411 is what I have shown the sample. In the similar way, we need to compute for 8, 4, 13, 5, 7, 14. And for 4, 11, the value of the principal component is minus 4.3052. Here, the next step is, step 6 is to transform the data. The final step is to transform the original data into the lower dimensional space defined by the principal components. Here, in this picture, we could see the various data points. The data points are plotted and this is showing the mean. And in this picture, we are shifting the origin and we are changing the directions of the coordinate axis to the directions of the eigenvectors E1 and E2. E1 is the eigenvector of the corresponding eigenvalue lambda 1. And this picture, we are dropping the perpendiculars from the given data points 4, 11, 8, 4, 7, 14, 13, 5 to the E1 axis. This picture, as you could see, we have reduced the dimension. This is the one-dimensional approximation of the data set. We have transformed the values, the data values. In this video, we have learnt about the principal component analysis. Thank you.